Good morning. Thank you to everybody. I am presenting now some new results. We tried to combine two residues, agricultural residues and industrial residues, to produce fertilizer for sustainable agriculture. My study started in cooperation with the Steel Belt System, that is an engineering and production company. Its location in Milan, but is widespread over the world, and it is specialized in the design and manufacturing of steel belt system for industrial processes. But this industry is also pioneers in developing flaking and pastillating units for a wide range of products. What was my duty in this project? My duty was to support and to help the steel belt system from a scientific point of view in converting harmful wastes in resource. We used agricultural waste and elemental sulfur, and we identified the right size and shape of the new products for agricultural products to be more effective as a fertilizer. Why elemental sulfur and agricultural waste? Because elemental sulfur obtained from the residues of the desulfurization of natural gas and oil is a pollutant for the environment and is harmful for human health. Nowadays, a small part of this sulfur is used to produce new products. A small part is used for industrial process to produce sulfuric acid, another part to produce fertilizers such as ammonium sulfate fertilizer, chemical fertilizer, but the majority of sulfur is disposed in a specific area because it is subject to specific regulation to be disposed. Agriculture waste, in particular olive waste, orange residues, because are the main recalcitrant biomass produced in the Mediterranean countries, are pollutant for the environment, and there are strict rules to dispose this waste. What we did, the sulfur, if I want to use sulfur for agricultural purpose, I cannot use elemental sulfur because it is insoluble in water, and generally it's not kept in soil by soil colloids, so it's leached. So I need to use sulfur linked with an inert substrate, in this case clay, and we used bentonite. To form a pellet. When the clay becomes wet in soil, it swells, breaks, and release sulfur. The released sulfur needs to be transformed to be oxidated by soil microbial biomass to produce sulfate. That is the form that the plant takes up. Of course, the rate of oxidation depends on the soil property, the environmental condition, but mainly by the shape and the size of the pellet that you produce. What is the novelty of this study? The novelty of this study is not specific to form and to produce sulfur bentonite, because if you go in the market, you can find some other industry that's produce sulfur bentonite, but as granules. But is to identify the right size and shape of sulfur bentonite and to link this sulfur bentonite to organic waste, to have a combination of corrective and organic fertilizer, with the dual aim to improve the quality and fertility of alkaline soil, because sulfur lowers the pH of alkaline soil, and also to increase plant productivity. This is a brief introduction to the sulfur process that steel belt system carry on, and it starts from liquid sulfur to produce solid sulfur, and then fertilizer or sulfur for other application. We focalized our attention on fertilizer production. What we did, we produced the pastilles. In this case, we started to test flakes, pastilles, and granules, but pastilles is the best shapes, with 90% of sulfur and 10% of bentonite. And then the more suitable size is between 2 and 4 millimeter. This is the difference from pastilles and granules that you can find in the market. Pastille is a flat size, so interact better with the soil surface and become quickly wet and breaks easily. And the better size is between 2 and 4 millimeter because it's quickly to breaks. Then, after this first part, we pastilled the sulfur bentonite and linked this one with agriculture waste, dried orange residues and dried olive residues in a percentage of 5%. Then we started with our experiment on soil to see if we have a benefit for soil from a biological point of view. And we used an alkaline soils to see if our pastilles were able to lower the pH, and amended this soil with sulfur bentonite, with orange waste, with olive waste, and sulfur bentonite alone. The concentration that we used is 0.88 gram liter, that correspond to ammonium sulfite fertilizer used at a concentration of 600 kilo per hectare, with a 20% of sulfurous title. And this is the most common fertilizer used containing sulfur. The soil in pot was regularly watered to maintain 7% of field capacity, to have the possibility to wet the clay, and also to have the right humidity for the microbial biomass. Our results after 2 months of treatment on biochemical parameters showed that all the treatment was better than control because they was able to lower the pH, and the treatment A is the best one because not only lowered more than the other the pH, but also increased the organic matter, the microbial biomass, nitrogen, and the microbial activity, as indicator that FDA, that's flourishing deacetate hydrolysis, that is an indicator of microbial activity in soil. Then we conducted also 2 different experiments on plants. The first one in vitro to test the phytotoxicity of these pastilles in petri dish, in growth chamber, and we used 2 different species, target species, red onion and bean, and legumes also. And then in pots for 3 months in glass house on the same species, and we added the chili pepper, that is a species that generally grow in the west country, where we find a lot of alkaline soils. And we tested the growth and phenotypic parameters. The in vitro experiment was carried on for 9 days in growth chamber, and we tested germination and also root and shoot length. And we used the 3 different pastilles with different concentration to identify the best concentration that stimulated germination. The results showed that the first one on red onion, that increasing the concentration, we have a delay of germination up to 0.88 gram per liter. That is the best concentration that we also add on soil properties. We have the total final germination, and also we have a good result in growth, root growth, and shoot growth. The A treatment with orange waste is the best one in inducing germination, root, and shoot growth. As you can see from this picture, you can see the different treatment, and the A treatment is a good balance between root and shoot length, and the best growth also. Then we have red bean, and our treatment showed that also the 0.88 is the best concentration in inducing germination or root and shoot growth. In this case, we have also A, that is good in inducing a root and shoot elongation, but even B is good in inducing root elongation, even we have a shorter shoot. You can see this one in the picture, but what is interesting to notice that even if A is better in inducing root and shoot growth, B is better in inducing a better root morphology, because we have thicker roots in comparison to A, and a best root architecture that may be that in the future may be better for the growth of plants. Then we started with pot experiment. Of course, we selected the one concentration only, the best concentration that induced the best results on soil and the best result on in vitro study. That is 0.88 gram per liter. Our control was not amended soil, and we used an alkaline soil, of course. The plants were regularly watered to maintain 7% of field capacity. And our result showed that we have on red onion, after 3 months, the best result with the treatment A plus orange waste, and we confirmed the test of phytotoxicity in vitro. And we have the best plant growth, leaf number, and also fruit size. And you can see that the best growth with the plants is with treatment A, and the best root, fruits that we obtained was with treatment A. We have a big size of fruit in comparison to the other treatment, also in comparison to the control. But all the treatments are better than control, both in plant growth that in fruit size. Then we have the bean, and the best growth of the bean in this case is with the treatment B. That is a bit different from the in vitro study. It seemed the treatment A, but B at the end, in the late stage, is better. Maybe because they induced the better root architecture and the plant absorbed by roots. So we have a more surface as a root to absorb other nutrients. And you can see this one in this picture that the treatment B is better. We have better fruit as a number as length. The last one is chili pepper, and we have that the best treatment is the treatment A, but all the treatments are better than control. We have the best growth of the plant, and you can see in this picture that the plant is much better with treatment A. All the treatments are better than control, even C, because it has a wider surface leaf area. At the end of this treatment, we wanted to test the performance of the plant from a photosynthetic point of view. We tested the photosynthetic efficiency in respect to control of the treated plant by using an imaging pump chlorophyll fluorometer system. And this is an example of a picture that is show the activity or reaction center in the photosystem 2. The clear area are the inactivated center. And you can see that, for example, this is for bean, on an example, that in the bean, the bee treatment, we have a more active area, less clear area, so it's more active, this photosystem too. In this, I don't want to bore you explaining each results, but only few that are important in explaining the photosystem efficiency of the plants. If you can see, the first one is the Epson2, it is related to the transformation of photochemical energy in chemical energy. So you have more chemical energy, more carbon that is fixed. And in this case, this range between 0 and 1 as the indicator, and we have the best result with the treatment because this value is higher. Then we have the indicator Epson NPQ, that is an indicator of photon flux density. Higher value show that we can have a photooxidation. In this case, we have a lower value than control, so our treatment is good, not cause a reactive oxygen species in the plant. And the Epson NO is related to the mechanism protective of the photosystem, related to xanthophyll and carotenoid. Higher value indicate that this is not good in defend plants. So we have a lower value. So this means that the plant is a good protective mechanism against external agent. This is related to electron transport rate. We have a good transport rate because the rate is higher than control. And the last one that I show you is the FB-FM ratio. That is related to the reaction activity of reaction center of the photosystem. In this case, we have a value higher in presence of the treatment. This means that our treated plant have a perfect photosystem efficiency. But why we obtain the difference between the treatment that we produce, the pastilles, even if the sulfur amount is more or less the same? In this case, we decided to test the chemical characteristic of the single pastilles that we obtained to see if we have some difference. And as we can see in this picture, we have difference. The treatment A that seems the best one on soil and plant has a lower pH and lower EC, but a good amount of water-soluble phenols that may represent a carbon source for the reproduction of a microbial biomass in soil, no ammonium, less sodium, a good amount of potassium and magnesium. So may add value to the pastilles for the plant growth and microbial reproduction. So our conclusion in this case are that the sulfur bentonite, if used alone, may be a good corrective fertilizer. If used in combination with agricultural waste, may be a corrective nutritional fertilizer. The best shape is the pastilles because it breaks in a short time, and the best size is 2 to 4 millimeter. The easy disintegration allow a rapid correction of the soil pH, and in this case improve quickly the cultivability of alkaline and saline soil. The lowering of the pH value in the root area permit the absorption of the other nutrient that is important for plant growth. And the addition of agricultural waste to sulfur bentonite, in particular of orange waste, improve the fertilizer power of sulfur bentonite. We can also say that we found a relationship between the species and the type of fertilizer that we used, and also that the effect that we found at early stage are different from that we can find at late stage. So it's important to follow all the cycle of plants. We can say that the waste material, both agricultural and industrial, may represent a resource for the recovery of saline and alkaline soil, and an additional incoming, for example, for agriculture sector, because the agricultural waste may be used to produce fertilizer. We have also work in progress that we are analyzing the nutraceutical properties of fruit that we obtained to see if the fertilizer are able to improve soil fertility and plant growth, but also the nutraceutical properties of our fruits. Thank you very much for your attention.
If anyone has any questions, please. I would like to ask you, have you tried a different bentonite or not using bentonite, just the residues and the sulfur?
Yes, when you don't use bentonite, we pastilles only sulfur. You don't have any results because the pastilles remain as such in soil. You don't have a release. 6 months we waited, but we don't have any results. No pH lower. So we can try other clay, but I think we are trying to increase the amount of organic material in respect to clay to see if the organic material can link the sulfur, so to reduce the clay and to increase organic material. This is better orange in increasing the organic matter, but we are work in progress.
Thank you.